Okay, want to look at this problem. And what we see is that this equation is not exact. So we just put it in the form mdx plus ndy, where this expression is supposed to represent the differential of some function f that we want to find. If it does represent the differential of f, then m is the x derivative of f, and n is the y derivative, and it follows by the fact that fxy equals fyx, that my and nx would have to be the same, but my is equal to 2y and nx is just equal to y. This equation isn't exact. So we want to see if we can find an integrating factor mu of xy such that mu m plus mu n equals 0 is exact. Now that means that you're going to have u times this, and actually when I did the nx, got negative y, right? Anyhow, so that mu times this is exact. Okay, well, the derivative of this with respect to y is equal to this derivative of the n function, the my equal to the nx, if m is now this with the integrating factor, okay? Well, the derivative of this with respect to y is first mu y times this plus mu times the y derivative of this. And that should equal mu x, and I'll bring the negative sign out here. And maybe just make that minus u times y. Okay, so we're looking for a mu that does this. This tells us that mu y times x squared plus y squared minus 3 plus mu x times y plus xy, putting all the derivatives of mu over here, is equal to going blind here, equal to whatever we have left, which is going to be this. Put this term over on this side. You get negative 2 mu y, and then you get a negative mu y, which of course is negative 3 mu y. Now there's cause for joy over here. and it's not 2 mu y. Not sure what's going on in my brain here, but it's obviously still pretty flexible because I keep coming up with new ways to write things down wrong. Okay, it's mu times negative 2y minus y, which would be negative 3 mu y. Okay, well, this is a partial differential equation. It involves both derivatives of mu with respect to y and partials of mu with respect to y and with respect to x. We're not equipped to do that. We're not going to be able to solve equations of this nature in this course. That's a later course, a later effort, a later thing to learn. If you go that far in your mathematics, and that'll depend on what field of engineering you happen to go into, and just how ambitious you want to be with your mathematics. So if we assume what? Okay, well, over here, we get just a function of y. So we could assume that mu is just a function of y. Then mu could be written just as d mu dy or mu prime. Now we're down pretty low on the board here. And I don't know, the watermark might interfere with this because it comes over about here, I think. So let's get down a little lower so we can read that. Okay, so mu y can be written as just d mu dy or mu prime. So our equation just becomes mu prime times x squared plus y squared minus 3 equals mu times 2y minus y divided by the x squared plus y squared minus 3. Now I've done the clever thing. I've cut one board in half, so I don't end up writing stuff over here where you can't see it. And I also end up writing a little bigger over here because for some reason I tend to write smaller as I get to the left side of the board, which exacerbates the fact that the side of the board is further from the camera and at a bit of an inconvenient angle. Okay, so we have this, and then we can write this equation as if we also note that mu x is 0, if mu is just a function of y, then we just have this term equals this. So we have thus up here where you can't see it. So let's raise the camera a little bit. Equation becomes mu prime times x squared plus y squared minus 3 equals negative 3 y, there it is. 2y minus 3y is negative 3y. Okay, minus 3y times mu. Now, if we look at this equation, it's first order linear. Okay, just wanting it to become separable, but it isn't. But let's just say, okay. We could write it as d mu dy equals, sorry, plus 3y over x squared plus y squared minus 3 times mu equals 0. But something has apparently not worked out because this isn't a function just of x. So let's say first order linear. It's not of this form. So it's not first order linear. So we could try assuming that mu is a function of x. Then we get here could have written that as negative 3y mu. Okay, we get this because then mu y would be 0. And then mu x could be written as mu prime. And as a derivative, not a partial derivative, so d mu dx is negative 3y mu. So that partial of mu with respect to mu is negative 3y dx. So it's the natural log of the absolute value of mu negative 3xy. We could add a constant, but there's no reason to. So that mu could be e to the negative 3xy. Multiplying then both sides of the original equation by e to the negative 3xy, if I've done this correctly, which is always questionable, we should get an exact equation. Okay, well, if that's so, then we come to the question, is mu multiplied through by this equation exact? Okay, well, you take the y derivative of this, the x derivative of this, see if they're equal. I'm skeptical, but let's see. So is this y derivative of the m function equal to the x derivative? Minus sign bothers me. You've got to get a minus sign both ways. Maybe I have the equation backwards or something. Is this equal to this? Now the y derivative of this is going to be negative 3x times x squared plus y squared minus 3. This times e to the x. So I'm just going to do e to the negative 3xy out in front, since it's going to occur in both of my derivatives. And then it's going to be this plus 2y equal to e to the negative 3xy, and the x derivative of this is y. And we're going to have negative. And then plus the derivative, x derivative of this, which is going to be y. That's going to give me 0. No, it isn't, because I'm going to get a 3 here. Okay. Now the 3xy doesn't matter. But if I multiply all this out, it doesn't work worth a hoot, because I'm going to get x terms here as well as y terms. So something went haywire, and I'm not going to try to go back and reconcile it, but that is the process. Well, if I can remember not to erase these boards, I'll go back and see what happens. Is that pretty much the process you followed? We want to talk about homogeneous equations. First of all, homogeneous expression. Just the idea of what homogeneous means. xy squared plus y cubed minus 3x squared y is homogeneous because every term is of degree 3. This is a polynomial, of course it's a degree 3 polynomial because every term is of degree 3. It's a polynomial in 2 variables, x and y. But you see that the degree of y here is 2, the degree of x is 1, so the total degree is 1 and 2, which is 3. Total degree here is obviously 3, and total degree here is again second degree in x, first degree in y, degree is 3. So let's just call this P of x. Okay, well, the book uses alpha. I've always used T, but I'll go with the book. P of x, y. So P of alpha x, alpha y equals alpha x times alpha y squared plus alpha y cubed minus 3 times alpha x squared times alpha y. Well, if I work that out, very simply, you do in your head. You're going to get an alpha and an alpha squared here. So you get alpha cubed xy plus alpha cubed y minus 3 alpha cubed x squared y, which is alpha cubed can be factored out of all this. And what you got left is just xy here. X it should be an xy squared. Xy squared, what you got here. A y cubed, what you got here. I'm focused on the alpha apparently. And then minus 3 x squared y here. So it's alpha cubed times P of xy. So we say that this is homogeneous of degree 3. So we have a homogeneous equation of degree 3. Okay, well, if dy dx equals f of xy, yeah, my sentence isn't working out. One of these is a U, homogeneous of degree n, and not sure how far I want to go with this. then u equals x over y or u equals y over x. Substitution makes the equation separable. And once more, it might be that one substitution or the other gives you the simpler integral because, of course, you integrate a separable equation to solve it. Okay, well, there we have it. Because of time factors, I don't want to develop the whole theory of it, but you can look at it in the book and we can maybe talk about it next time. So I realize that I don't have a great example, but I think if I just use this from my right-hand side, I'll have an example that'll be illustrative. Should have thought that out in advance, but I didn't. So let's consider the equation. Yes. This is homogeneous of degree 3. So we're going to let u equal x over y. So y equals u times x. And dy equals let's write dy dx equals, we'll write ux times x, derivative of this times this, plus u. Well, now if we substitute this in for dy dx, we get x. Du dx plus u equals what? X y squared, but y equals ux. And you know what? Ux and u sub x are a little confusing. So I'm going to write this as du dx. There's nothing wrong with what I wrote there, except it might be a little confusing. I can use this notation, and then it's no longer confusing. Okay? So x times du dx, I'm sorry, I got the du dx over here. Sorry, du dx again is u times x squared. And let me write that down carefully. Okay. Y is ux. So x y squared is, let's write it out carefully, ux well, x times ux squared, okay? And then y cubed is ux cubed, and then minus 3x squared times ux. So this is then x cubed times u squared, and this is x cubed times u cubed, and this is minus 3x cubed times u. I see how this has worked out. This is homogeneous of degree 3, and we're getting an x cubed term in each of these. Now that's because we're letting u equal x over y, so that y equals ux. And if you look at how the substitution works, you see how it's inevitable that this is going to occur. Now, why is this a great thing? So, well, now something's a little bit haywire here, not unusual. Right-hand side just this, it's separable. We'll throw that u in there. And then divide by x. Dividing by x would be no problem, but having that u in there is not going to make it separable. So I've got to stop and think about that a little bit, see if I made an error. Separable? No. Should be. And I have to go back to proof. I'll post a little addendum on this. But it's not separable. Okay, should have been, and should have. Ended up with something that works. In general, the form of a separable equation or of a homogeneous equation would be like m dx plus n dy equals 0. And homogeneous if m and n are both homogeneous of the same degree, which means that I had a brain glitch, whatever you want to call it, when I jumped to this conclusion that this equation is homogeneous. It's not. It would have to have a denominator over here that's homogeneous of the same degree. Okay, so what I did would have worked. I'd have just done something like this. Okay, that'll be homogeneous at degree 3. And now when you do this, things work out. Don't have time to work that one out, but I will do my best to work that one out if I don't erase the board. Even if I do, I can go back to the video, but it takes a while for it to process. And I'll go ahead and work that one out. So apologize. Should have gone to this form in the beginning, but when I started with the idea of a homogeneous expression, I wrote this down carelessly, blindly went ahead and proved that it didn't work. But it does if your numerator and denominator are homogeneous to the same degree. And that's equivalent to this because, well, I'm pointing to this as the equation. This is homogeneous of degree 0. Numerator and denominator are both homogeneous. And then when I wrote down this equation, that's where I should have written down a denominator homogeneous to the same degree, like and if you just turn the crank from here to here, you do end up with a separate equation. If you go back to this form, then the condition's much more obvious. And I certainly should have done that. Okay. Okay, I'm running short in board space. Ooh. Deal with this. Yep, I've used that. I've used this. The problem is there's something I want to retain from my previous class. So I don't want to use these. Anyhow, I'm going to go to G. No, we're not. Okay. Let's see if I can get this one right. The Bernoulli equation has a form that's a lot like a linear equation. So it might just start with it. dy dx plus p of x, y. And of course, if over on this side I have some function of x, let's just say this is x squared, then I can just do my e to the negative integral p of x dx factor. Luke uses a capital P there. I like using lower p. So the capital P is the antiderivative of this. And e to the negative antiderivative is an integrating factor, and everything works out if you do the integrals. Okay, that's linear. But now we throw some power of y in here. And I'm saying the form is this, and making this a specific function of x. It doesn't give you a form, it gives you an example. And I forget what your book uses, but I generally use q of x. Okay. Write it this way. This is your linear equation in the form of a Bernoulli is same left-hand side. So it looks just like a linear equation, except that now Just debating whether to use N or M for this, but yeah, your book, I'm pretty sure uses M. It uses M. Okay, so here's your Bernoulli form. Now, every year when I teach this course, I derive this. Okay, and I'm going to say, I'm just going to give you the transformation. If we have time, I'll do the derivation, because I always love to do the derivation because there's a step in there with the algebra. It's really easy to confuse the laws of exponents. And I'm real prone to doing that, so I got to be careful. That's kind of a test whether I become completely senile, whether I can do it without making that error. Okay, straightforward idea. Okay, if, I believe your book uses U for this. Okay, the book I used before, we used V, so forgive me if I kind of screw that up, but if U equals y to the 1 minus n, then the equation's linear in the variables x and u. Okay, let's see how this works out. Suppose we have I'm a little hesitant to use e to the x. So I'm just going to use a power. And then over here, I'm going to have a y squared. Okay, this is Bernoulli. You have your p of x function in front of y, that's just x. And over here, you have a q of x in front of a power of y, square root of x times y squared. Okay, so n equals 2 power of y, and u is going to equal y to the 1 minus n equals y to the 1 minus 2 equals y to the negative 1, or 1 over y. It follows. Now we want to do the substitution, okay? Actually, what we want to get is we want to get all the y's out of this equation and get u's. So we're going to want a du dx, we're going to want some function of u here, some function of u over here. Well, and just look at the position of the camera. Get a little lower so the watermarks don't screw things up. Okay, thus, in this case, y equals 1 over u. And by the chain rule, dy dx is your negative 1 over u squared, but u is a function of x. So you're going to have a du dx there. So that this term can be replaced by negative 1 over u squared du dx. The y here, of course, is just going to be 1 over u, and the y squared is going to be 1 over u squared. So the equation becomes I'm going to rewrite this bigger on another board, but wrote it kind of small here. Okay, what? Now dy dx is this, so there it is. Plus your x times y. Y is 1 over u, so this is x over u. And then it's going to be square root of x times 1 over u squared. This means when I multiply through by u, I'm not going to have a u over here. I'm just going to have a square root of x. So this is a function of x, which is consistent with the form of a linear equation. And over here, I'm going to have a ux. It'll be a negative ux, but you understand, it's just going to be a function of u times x. And as a matter of fact, it's going to be it's going to be minus ux. And it's not going to be general, so I'm not going to say what I was going to say. Anyhow, you got this. If we multiply through by the negative u squared, we're going to get the form of a linear. Okay, so let me manage these boards a little bit. So what I get down here, I bring up to the top, and I'm going to rewrite it. What we're shown here is that. Okay. If u equals 1 over y, equation dy dx plus yx, isn't it? Yeah. I'll just write that's square root of xy squared. Okay, just by following through the substitution, this becomes an equation that you can almost see down here. I think I might have a negative 1 over u squared there. Let's see. No, y is 1 over u. Okay. Okay. So that's what we've accomplished by the substitution. And all you got to remember is that you let u equal y to the 1 minus n when the equation's in this form. Okay, now we can solve this equation. Okay. So what we do, we multiply. I don't have room to write both sides, but we multiply through this equation by negative u squared. And we get du dx minus xu equals square root of x. Because, of course, and it's negative. Multiplying through by negative u squared here gives us negative square root of x. And that's a pretty simple first order linear non-homogeneous equation. With the integrating factor, I assume you know how to do that. And if you don't, I'm not going to write it out for you. I'll tell you to review it because you got to keep it in your mind. Integrating factor, and I'm probably going to write it wrong, but it's going to be e to the negative x squared over 2. Okay, because we just integrate this, and actually it's the negative square root of x squared over 2. I told you I was going to screw it up. And that's going to be e to the x squared over 2. So we write e to the x squared over 2 du dx minus x e to the x squared over 2 u equals negative square root of x e to the x squared over 2, which is going to end up not being integrable. I go back and change it so that it is integrable. If I hadn't put that square root on the x, then I'd been able to integrate it, and I could have done that. And I could have thought that far through, but I didn't. So maybe I'm going to go back and take that square root off, but let's just see how it works with the square root on there. So this side is going to give us a negative. And plus there, got a minus there, so it is minus, and that's going to be minus. We are going to have opposite signs. I'm going to integrate. Okay, I put too many negative signs on my integrating factor. No, I didn't, because the integrating factor becomes negative. There. Seem to be living in a mistake-prone world. Let's make sure. We want to check this. Okay. Is this the differential of e to the x squared over 2 times u? Okay. And that differential is going to have a negative sign here. It's going to be okay, derivative of this times u. And then this, and this should match this sign. And I don't see how that negative sign came in there. If this is plus, then everything would match. So I'm going to pause a minute, see if I can find that. Okay, something's wrong. This should be something like, just give or take a minus sign somewhere. this, and your u is just going to be this. Now, it's not an integral you can do. And something's wrong, so that's not really going to be the solution. But that's the way it should have worked out. Something very much like that. Now, I'll observe that you can't perform that integral. Okay, that's not integrable. Had I not put a square root on this x, then I wouldn't have had a square root on this x. Meaning I wouldn't have a square root on this x, or 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 this x. Which means I could have integrated this by simple u substitution, simple substitution, like another u or v or something equal x squared over 2, and this becomes an integral of e to the v times a constant dv. So very simple to integrate. But I don't think there's a way to torture this integral. I think doing this integral would be equivalent to integrating e to the x squared, which can't be done. Okay, well, something's wrong. But if this is integrable and so forth, u equals this. And remember that u was y to the 1 minus m. So we would get this, and I'm going to lower the camera so you'll be able to read this. So y should be the reciprocal of this. Well, y is going to be e to the x squared over 2 divided by this integral. And then you could take that, if you could integrate this, and you can still do the derivative of the integral. Okay, you can use it. Second fundamental theorem, although it's not a definite integral. You can still substitute that. So if y equals the reciprocal of this, and hopefully with an integral you can do, you substitute back into the original equation, here it is, and verify it. So that's a method. Should have worked. I have to work out why it didn't. Okay, well, there's one more substitution. Fairly simple substitution. And I'm out of small boards that I can write on. I'm finding I kind of like that. Not being out of small boards, but using small boards. These things are blocking my foot. See if we can get it out of the way. Okay. So now, dy dx equals f of some function that's linear in x and y. Let u equal that linear function. And your equation becomes separable. Example. Dy dx equals 2x minus 3y plus 7. It's not the least bit separable. But let u let u equal 2x minus 3y plus 7. So that y equals u minus 2x minus 7 so that dy dx is du dx minus 2 and then you get du dx minus 2, which is dy dx. Du dx minus 2 equals u. Now, whatever linear function you use, when you solve it for y, you're going to have just some multiple of x over here, because linear function can only contain just a multiple of x. So that when you do your dy dx after solving for y, you are always going to get a du dx, and you're going to get whatever the coefficient of x is as a constant. So it's always going to work out like this, so that du dx equals u plus 2. And normally I'd write it over here, but that's where it gets really hard to read. And when I get over here, I usually don't have a lot of space. I start writing small without realizing it. We don't want to do that. So if I do this, we get du over u plus 2 equals dx, which means that the natural log of the absolute value of u plus 2 will equal x. We'll put the integration constant in this time, so that u plus 2 now we've done this a lot of times before. It's going to be e to the x plus c, which is e to the c, e to the x, where c is any constant. And you get u equals a e to the x plus a constant, which means the 2x minus 3y plus 7. equals this. And then we solve for y. Just subtract 2x from both sides, subtract 7 from both sides, divide by -3. So I'm just going to say y equals, etc. This is very slick, and it's something you encounter. That's something you're going to have to do for homework, but it always works out very similar to this. Steps are always going to pretty much be the same. So it's the simplest of the three, and maybe the only one I got right. Substitutions. Homogeneous equation, Bernoulli equation. And incidentally, your book does something that's totally illiterate. And I don't mean to throw stones at this guy's written an outstanding book. I love it. And he has insights that I've always wanted to use very explicitly. But they've never been expressed as nicely as they have in this textbook. Okay, so I'm not throwing stones, but when he uses the heading for this, he said Bernoulli's equation. Well, Bernoulli's equation, I'll just write it down here. Something else didn't work, why not? Is the expression of conservation of energy for a fluid. It's going to be rho gy plus 1/2 rho v squared. Potential energy term, kinetic energy term, and then your work term. And that's equal to a constant. It's work per unit volume. Okay, so that's potential energy, that's kinetic energy. This is work per unit volume. And that's Bernoulli's equation. It's nothing like this. And the only thing they have in common is that these equations were derived and or publicized by or used by one of the Bernoullis. Okay, Jacob Bernoulli, very famous Bernoulli, there are a bunch of them. There's Jacob, there's Billy Bob, there was Joe Bob. Anyhow, there's a family of Bernoullis and over at least 3 generations, I believe. And I'm not even sure which Bernoulli is associated with which equation, but I'm pretty sure they all knew all of them. So the heading should have been Bernoulli equations, not Bernoulli's equation. So, little critique there. And if I'm wrong about that, because I am totally illiterate about some things, but I don't think about this, somebody's welcome to point it out to me. Yes. Editors should have caught that, and it should never have been written that way in the first place. Okay, so not throwing any stones at an excellent author with an excellent book, just pointing out the only error I've found in the book. And of course, I make plenty of errors myself. Okay, any questions?